Hey everyone, and welcome back to The Explainer. Today, we're looking at a scenario that almost sounds like a glitch in the Matrix. What do you do when a ship is simply too long for the shipyard it's being built in? Well, the solution is pretty audacious. You literally build it in two completely separate halves. We're talking about a mind-boggling maritime engineering feat where shipbuilders have to battle physics, extreme logistics, and the chaotic ocean itself. When human ambition outgrows the physical Earth we build on, things get really interesting.
Okay, let's dive into this massive logistical headache. Picture this. A shipyard wins a super lucrative contract to build a megaship. Maybe it's a massive container vessel, maybe a supertanker. The design length of this beast is 380 meters. But there's a major catch. Their physical building dock, the giant dry basin where they actually lay the keel and assemble all the steel blocks, is only 300 meters long.
So we arrive at this ultimate question. How do you build the impossible? I mean, how exactly do engineers overcome an 80-meter discrepancy without, expanding their real estate, dropping billions on a brand new dry dock, or just walking away from the order entirely? You obviously can't just leave a huge chunk of a ship hanging out over the water while you weld it.
Section 1. When ships outgrow shipyards. 80 meters, that is the gap we are dealing with here. To put that into perspective, that's roughly the length of a standard city block. And in the world of shipbuilding, being 80 meters short is a complete deal breaker for normal conventional construction. It literally means the ship simply cannot be assembled in one piece on land or in a single dry dock. The shipyard is officially out of room. Section 2. The split construction solution.
So here is the audacious fix. You build the ship in two completely separate pieces. Instead of one long, continuous construction process, the shipyard builds the aft section, which is usually where the heavy machinery and the engine room sit, and they build the forward section totally separately. They finish each of these sections to an incredibly high degree. Then they actually float both halves out of the dock and bring them together right out there in the harbor. Typically, this massive join is made just forward of midships.
Section 3. Welding beneath the waves.
To pull this off, engineers use something called a cofferdam. If you aren't familiar, these are basically temporary watertight boxes built right around the outside of the joint, on each half of the hull. They are meticulously designed to seal perfectly against the steel hull plating. It's a bit of an obscure piece of engineering tech, but it is absolutely vital. See, the crucial joint connecting these two halves is entirely underwater, which means the workers have to perform critical structural welding at and below the waterline.
So how does this system actually create a functional workspace? Well, first, temporary bulkheads are sealed tight to keep the two ship halves buoyant. Next, those massive watertight boxes, the cofferdams, are bolted on around the outside of the joint. Step 3, powerful pumps suck all the water out from inside the cofferdam. And finally, step 4, workers literally climb down through hatches into the space. They are now standing below the surface of the ocean, in a claustrophobic but entirely dry workspace, getting ready to perform the heavy-duty structural welding that's going to make the ship whole.
Section 4. The Ultimate Alignment Challenge.
Now get a load of this. The microscopic margin for error we are talking about here is just 10 millimeters. When mating these two halves, the straightness of the keel line across the entire joint has to hit a target tolerance of within 10 millimeters. Just think about that for a second. You have a floating 380-meter steel leviathan weighing tens of thousands of tons, and the allowable deviation is literally less than the width of your finger. It is exactly like trying to parallel park a skyscraper.
And to make matters even more complicated, just look at the chaotic forces working against these engineers. In a dry dock, everything is static. It's perfectly controlled, just like the original 3D CAD designs. But out in the harbor, you're dealing with the harsh reality of the ocean. Wave action is constantly bumping the two halves around. The tide is shifting up and down. Plus, you have these massive buoyancy forces distributing weight unevenly across the two floating structures. Getting this join to strict tolerances before any structural welds are made is, for sure, arguably the most demanding alignment operation in all of shipbuilding.
Which brings us to this really incredible quote from DJ Ayers in his textbook Ship Construction. He notes, to balance any tendency for the vessel to hog during the pumping of the cofferdam, it is necessary to shift ballast in the fore and aft sections. Now, hogging is just an engineering term for when a ship bends with the middle pushing up and the ends drooping down. This happens because of unbalanced weight and buoyancy.
If they aren't incredibly careful, just pumping the water out of the cofferdam can change the buoyancy locally and actually bend the ship, causing a complete structural catastrophe before the weld is even finished. So engineers have to constantly pump water ballast back and forth inside the two ship halves to perfectly counteract those bending forces.
To conquer all this chaos, the shipyard relies on a serious precision toolkit. Survey teams use highly sensitive optical instruments to measure the alignment down to the literal millimeter. Heavy tackles and super powerful hydraulic jacks are then used to physically force the massive steel hulls into perfect alignment. All the while, that water ballast we just talked about is shifting to keep buoyancy neutral. And once it's perfectly lined and welded, every single inch of that critical joint is rigorously tested using X-rays, just to ensure absolute structural integrity.
Section 5. Ready for the sea.
The takeaway here is huge. By mastering the technique of split construction and joining halves afloat, shipyards are no longer limited by their physical real estate. They don't need a 400-meter dry dock to build a 380-meter ship. This specific engineering triumph physically expands the limits of global trade. It allows shipbuilders to construct the massive mega-fleets of tomorrow without being boxed in by the concrete walls of yesterday. So, I want to end the explainer today with a slightly provocative thought. If we can join floating megaships to millimeter precision while actively battling the sea itself, what limits actually remain for the fleets of tomorrow? It really makes you wonder what engineers are going to come up with next when they're told something is impossible. But for now, the ship is structurally complete. Before launch, every weld and every structure must be proven. Section 4. Testing and commissioning.